Today we are going to discuss the topic least common multiple. The least common multiple of two positive integers a and b is the least positive integer divisible by both a and b. Least common multiple is denoted by this symbol, that is AB. This is LCM of AB, LCM of A and B. So LCM of two numbers A and B, as its name indicates, it is the least common multiple. For example, to evaluate the LCM of 18 and 24, we know the positive multiples of 18 are 18, 36, etc. That is, this is 1 into 18, this is 2 into 18, 3 into 18, 4 into 18, etc. These are the positive multiples of 18. Now the multiples of 24 are 24, and 2 into 24 is 48, 3 into 24 is 72, etc. So their common multiples are, that is multiples of 18 and 424 which are common are 72. 72 is a common multiple of 18 and 24. The next one is 124. 124 is a multiple of 18 and 124 is a multiple of 24 also. Next one is 216, etc. So the LCM of 18 and 24 is the least common multiple. It is 72. So 72 is the least common multiple of 18 and 24. Now we have the symbolic definition of LCM. The LCM of two positive integers a and b is the positive integer m such that a divides m and b divides m. That is the first property. That is a divides m, b divides m. That is m is a multiple of a and m is a multiple of b. Now if a divides m dash and b divides m dash, then m less than or equal to m dash, where m dash is a positive integer. That is, if m dash is a multiple of a and b, both a and b, then m should be less than or equal to this m dash. That is the least common multiple of a and b. Now we can find the LCM by using canonical decomposition of the numbers. If we have two numbers a and b, then we can use the canonical decomposition of a and b to find the LCM. Suppose we have to find the LCM of 90 and 168. We have the canonical decomposition of 90 is 2 into 3 square into 5. You can verify this. And canonical decomposition of 168 is 2 cube into 3 into 7. So we know the LCM is actually least common multiple. So considering the prime 2, here we have 2 power 1 and here we have 2 power 3. So least common multiple will have the factor 2 power 3. And considering the prime 3, so here we have 3 square and here we have 3. So the LCM will have the factor 3 square. Now considering the prime 5, here we have 5 power 1 and here we have 5 power 0. So in LCM we will have 5. Now next is 7. So here we have 7 power 0 and here we have 7 power 1. So power 1. So we have in LCM a factor 7. So the LCM is 2 power 3 into 3 square into 5 into 7. That is 2520. But if we are finding the GCD, we have, it is nothing but, if we are taking this, that is greatest common divisor. GCD is actually greatest common divisor. So common divisor is, here we have 2 only. Taking this 2, we have 2 into, this is 3 square and 3, so we have 3, and here we have 5 power 1 and 5 power 0, that is we are taking 5 power 0 only. Then 7 power 0 and 7 power 1, here also we have taking 7 power 0 only. So we have 6 will be the GCD. Now from this we can see that it is the maximum of, that is the LCM of 90 and 168 is equal to 2 cube 3 square 5 into 7, which is nothing but, from this we have 2 power maximum of 1 comma 3. 1 is actually the exponent of this and the 3 is exponent of this. So maximum of 1 comma 3 into 3 power maximum of 2 comma 1 into 5 power maximum of 1 comma 0, 7 power maximum of 0 comma 1. Okay, so we can generalize this result. Let a and b be two positive integers with the following canonical decomposition. That is, a equal to p1 power a1, p2 power a2, etc., pn power an, and b equal to p1 power b1, p2 power b2, etc., into pn power bn, where ai comma bi are greater than or equal to 0. Then the LCM of a comma b is nothing but p1 power maximum of a1 comma b1 into P2 power a maximum of A2, P2, etc. Pn into Pn power maximum of An, Bn. If you are finding the GCD, then it will be minimum of A1, B1, minimum of A2, P2, etc. For example, using the canonical decomposition of 1050 and 2574, find their LCM. So to find the LCM by using the canonical decomposition, first we have to find the canonical decomposition of 1050 and 2574. We know the canonical decomposition of 1050 equal to 2 into 3 into 5 square into 7, and canonical decomposition of 2574 is equal to 2 into 3 square into 11 into 13. You just verify this. So we have this is equal to 2 power 1, 3 power 1, 5 square, 7 power 1. Now we have 11 and 13 also. So 11, 11 power 0 and 13 power 0. And here we have 2 power 1, 3 square, then whatever 5, 5 power 0, 7 power 0, and 11 power 1, 13 power 1. So we have the LCM is nothing but 2 power maximum of 1 comma 1, maximum of 1 comma 1, and which is 1. 3 power maximum of 1 comma 2, which is equal to 2, that is 3 square. So 5 power maximum of 2 comma 0, that is 2. 7 power maximum of 1 comma 0, so it is 7 power 1. Then 11 power maximum of 0 comma 1, which is 11 power 1, and 13 power maximum of 0 comma 1, which is also 13 power 1. So multiplying these we will get the number 450450. That will be the LCM of these two numbers. Now we have a theorem. This theorem gives a connection or relation between the GCD and the LCM of two numbers. Let a and b be positive integers, then the LCM of a and b is equal to a into b divided by the GCD of a and b. Or we have ab is equal to LCM of a and b into GCD of a and b. Okay. For example, if you are taking numbers 18 and 24, we know the GCD of 18 and 24 is equal to 6, and LCM of 18 and 24 is equal to 72. You can verify this. Also, 6 into 72 equal to 18 into 24, or 6 into 72 is actually GCD into LCM. This is equal to 18 into 24, where 18 is actually our first number and 24 is our second number. So the GCD LCM of 18 and 24 is equal to 18 into 24 divided by the GCD of 18 and 24. Now we can try to prove this result. Let A equal to P1 power A1, P2 power A2, etc. Pn power An, and B equal to P1 power B1, P2 power B2, etc. Pn power Bn. Be the canonical decomposition of A and B respectively. Then we have the GCD of A comma B is nothing but P1 power minimum of A1 and B1 into P2 power minimum of A2 and B2, etc. Pn power minimum of An and Bn. Okay, we already know this. And the LCM of A and B is nothing but P1 power maximum of A1 and B1 into P2 power maximum of A2 and B2, etc. into Pn power maximum of An and Bn. Now, if you are multiplying these two, that is GCD of A and B and into LCM of A and B equal to this into this. Okay, this is the GCD and this is the LCM. So we have P1 power minimum of A1 B1 plus maximum of A1 B1. We are multiplying these two numbers. So P1 power minimum of this plus maximum of this into P2 power minimum of A2 B2 plus maximum of A2 B2, etc. into Pn power minimum of An Bn plus maximum of An Bn. Now we have this is nothing but P1 power A1 plus B1, because minimum of A1 B1 plus maximum of A1 B1 is equal to A1 plus B1 B1, because if A1 is the minimum, then B1 will be the maximum. Okay, so we will have A1 plus B1. Now if B1 is the minimum, then A1 will be the maximum. So then also we will get B1 plus A1, that is A1 plus B1. So we have P1 power A1 plus B1, P2 power, next one is P2 power A2 plus B2, etc. into Pn power An plus Bn. So we have, this is nothing but, this can be written as P1 power A1 into P1 power B1. P2 power A2, this is equal to P2 power A2 into P2 power B2. P2 power B2 into etc. Pn power An into Pn power Bn. So taking these powers, we have P1 power A1, P2 power A2, etc. Pn power An, which is nothing but A. And next one is P1 power B1, P2 power B2, P3 power B3, etc. Pn power Bn, which is nothing but B. So we have A into B. So the product of the GCD and the LCM is equal to the product of their that numbers. So we have the LCM A comma B is equal to AB divided by GCD of A and B. So this formula gives us a new method to find the LCM of two numbers if we know the GCD. If we know the GCD of two numbers, then we can directly for applying this, we get the LCM of that two numbers. Okay, so we have two methods to find the LCM. One method is by using the canonical decomposition, and second method is by using this formula. It is better to use this if we are given the GCD of that numbers. So using we have an example using the GCD of 252, 360, compute the LCM of 252, 360. So by the previous theorem, we have the LCM of 252 and 360 is equal to 252 into 360 divided by the GCD of 252 and 360. If we know this GCD, then we can directly apply this. Otherwise, we have to find the GCD like this. But this method is good if we know this GCD of these two numbers. Okay. Otherwise, it's better to use the previous method, that is by using the canonical decomposition. So, but in this question, we have to use this GCD to find the LCM. So, we are going to find the GCD first. So, we have the canonical decomposition of 252 is equal to 2 square, 3 square into 7, and that of 360 is equal to 2 cube into 3 square into 5. So from this we get the GCD is nothing but 2 square and 2 cube. So we have 2 square, 3 square, 3 square. So we have 3 square in GCD. Here is 7 and 5. So there are no common factors here. So it is GCD is equal to 36. Once we obtain this GCD, we can use LCM by finding this 252. LCM of these two numbers is equal to 252 into 360 divided by GCD of these two numbers. So GCD of these two numbers we obtain that 36. So this is 252 into 360 divided by 36. That is 2520. Now we have a corollary. Two positive integers a and b are relatively prime if and only if the LCM of a and b is equal to a into b. It is directly obtained from this theorem, because we have the LCM of A and B is equal to AB divided by GCD of A and B. But here we have, if they are relatively prime, and then we have AB equal to GCD of AB, A and B equal to 1. So we have from the previous theorem AB, LCM of AB is equal to A into B divided by GCD of AB, which is equal to AB divided by 1, that is AB. Also, the next direction also we can do like that. For example, we have 15 and 28 are relatively prime. So we have, by this theorem, we have the LCM of 15 and 28 is equal to 15 into 28, which is 420. Okay. Now we have a note. The idea of LCM can be extended to the three or more integers. For example, we have 24 is equal to 2 cube into 3, 28 equal to 2 square into 7, 36 equal to 2 square into 3 square. So the LCM of 24, 28 and 36 is equal to 2 power maximum of 3, 2 and 2, which is nothing but 3 into 3 power 1, 0 and 2. That is maximum of this is 2. Then 7 power 0, 1 and 0. 0, 1 and 0. The maximum of 0 and 1 and 0 is 1 itself. So it is 7 power 1. So this will be the GCD 504. Now we have theorem 3.18. Let a1, a2, etc. an be n positive integers where n is greater than or equal to 3. Then the LCM of a1, a2, etc. an is equal to LCM of a1, a2, etc. an minus 1, comma an. That is, we can find the LCM of more than two numbers recursively. Okay. For example, using recursion, evaluate the LCM of 24, 28, 36 and 40. Okay. We know by using the previous theorem, we have LCM of these four numbers is equal to the LCM of first three numbers and 40. Then we have this LCM of three numbers, that is the LCM of first two numbers and 36, then 40. So to find the LCM of these four numbers, we can just first find the LCM of these two numbers. So we have the LCM of 24 and 28 is equal to 168. You can verify this. It is 168. So we have 160 LCM of 168, 36. Now we can find the LCM of 168 and 36, which is nothing but for 504. This also you can verify. So we have this is equal to the LCM of 504 and 40, which is also you can verify this is equal to 2520. So the recursion can be used to find the LCM of more than two numbers. Okay. So we have a corollary of this theorem. If the positive integers a1, a2, etc. an are pairwise relatively prime, that is, we have ai aj is the GCD of ai aj is equal to 0 if I not equal to j. Then the LCM of a1, a2, etc. an is equal to a1 into a2 into etc. an minus 1 into a. For example, consider the numbers 12, 25 and 77, which are pairwise relatively prime because GCD of 12 and 25 is equal to 1. GCD of 12 and 77 is also 1. Also 25 and 77. GCD of 25 and 77 also 1. So these three numbers are pairwise relatively prime. So from the previous corollary, we have the LCM of these three numbers is equal to the product of these three numbers, that is 12 into 25 into 77, which is nothing but 23100. Now we have one more corollary. Let m1, m2, etc. mk and a be positive integers such that mi divides a for 1 less than or equal to I less than or equal to k. Then the LCM of m1, m2, etc. mk divides a. That means mi divides a means m1 divides a, m2 divides a, etc. mk divides a implies m1, m2, etc. mk. The LCM of m1, m2, etc. mk divides a. That is the corollary. So we can prove this by strong induction on k. The statement is clearly true when k equal to 1 and k equal to 2. That is, we have if m1 divides here, then the GCD m1 is actually divides here. So for k equal to 1. Now k equal to 2 means m1 divides here and m2 divides here. Implies LCM of m1 m2 divides here. That's also clear. Now assume that the result is true for integers 1 to t. That is, m1 divides a, m2 divides a, etc. mt divides a implies m1 LCM of m1, m2, etc. mt also divides a. That is the assumption. Now we have to show that the result is true for k equal to t plus 1. That is, we have to show that m1 divides a, m2 divides a, etc. mt divides a, comma mt plus 1 divides a implies m1, m2, etc. mt plus 1 divides a. Okay, so let mi divides a for 1 to k plus t plus 1. That is, m1 divides a, m1 divides a, m2 divides a, etc. mt divides a, and mt plus 1 divides a. Now we have to show that this implies LCM of m1, m2, etc. mt, comma mt plus 1 also divides a. So by this hypothesis, we are assumed this. By this assumption, we have m1, m2, etc. mk. That is the LCM of m1, m2, etc. mk divides a. Also, we have mt plus 1 divides a from this. Again, the hypothesis, we have the LCM of m1, m2, etc. mt, comma mt plus 1 is equal to divides a. That is, we have this is a number that is LCM of these numbers m1, m2, etc. mt, and mt plus 1 is again another number. So LCM of these LCM and this number is also divides a, because we have this divides a and this divides a. So we have the LCM of these two numbers. One number is this and the another number is this. It also divides a. So we have by the previous theorem 3.8, that is we have a LCM of m1, m2, etc. mt, comma mt plus 1 also divides a, because we have by recursion we have the LCM of this is actually LCM of m1, m2, etc. mt, comma mt plus 1. So this divides a means this divides a. So therefore this result is true for k equal to 3 plus 1. That is, the result is true for k equal to t plus 1. Therefore by induction the result is true for any positive integer k.